the structure and interpretation of computer programs bite-sized. 1.2.4 Exponentiation. Consider the problem of computing the exponential of a given number. We would like a procedure that takes as an argument a base b and positive integer exponent n and computes b raised to the n. One way to do this is via the recursive function. B of n equals b times b raised to n minus 1, and b of 0 is equal to 1, which translates readily into the procedure. Define the procedure for exponent b of n to be define the procedure exponent that takes inputs b and n to be if n is equal to 0, return 1. Otherwise, do multiply b and the exponent of b minus n, exponent of b so basically you apply exponent to b and then n minus 1 and then multiply that by b. And that's what you will return. And that's the recursive one. So we'll put that in the terminal here. And exponent. This is a linear recursive process which requires theta of n steps and theta of n space. Just as with factorial, we can readily formulate an equivalent linear iteration. Define the procedure exponent that takes inputs b and n to be the procedure exponent iter applied to b, n, and 1. Define exponent iteration, so exponent iteration is what I'm going to call it, exponent iter, iteration that takes inputs b, counter, and product to be if counter is equal to 0, return the product. Otherwise, apply the exponentiation iter procedure to b, and counter minus 1, and the product of b, multiply b and the product together. And so then those are your inputs to the exponentiation iter thing. So let's apply this one. Cool. This version requires theta of n steps and theta of 1 space. We can compute exponentials in fewer steps by using successive squaring. For instance, rather than computing b of 8 as b times b times b times b times b times b times b, so b's raised to the 8th, all that, we can compute it using 3 multiplications. B squared is b times b to the 4th is b squared times b squared, b to the 8th is b to the 4th times b to the 4th. This method of squaring works fine for exponents that are powers of 2. We can also take advantage of successive squaring in computing exponentials if we use the rule b of n is equal to b raised to, I think that's b, divided by b over 2 raised to the second if n is even, and b of n is b times b, and minus 1 if n is odd. Okay, we can define this method as a procedure. Define the procedure fast exponent that takes the inputs b and n to be conditional that check to see if n is equal to 0, return 1. If n is even, input n, and oh my goodness. If n is even, apply the square procedure to, and here, actually we'll just go from the middle out. So you divide n divided by 2, and then apply fast exponents to b and n divided by 2, and then square that whole thing. Otherwise, you do the other one we did, which is you take n minus 1, multiply n minus 1, apply fast exponent to b minus b and n minus 1, so you just put those two in for your inputs, and then multiply that by b, where the predicate to test whether an integer is defined in terms of the primitive procedure remainder by define even of n to equal, so the procedure even that takes input n is equal to the remainder of that takes inputs n and 2, and check and see if it's 0. Okay. The process evolved by fast exponent grows logarithmically with n in both space and number of steps. To see this, observe that computing b2 to the n, b raised to the 2n, using fast exponent requires only one more multiplication than computing b to the n. The size of the exponent we can compute therefore doubles approximately with every new multiplication we are allowed. Thus, the number of multiplications required for an exponent of n grows about as fast as the logarithm of n to the base 2. The process has theta log n growth. The difference between theta log n growth and theta n growth becomes striking as n becomes large. For example, fast exponent for n equals 1,000 requires only 14 multiplications. It is also possible to use the idea of successive squaring to devise an iterative algorithm that computes exponentials with a logarithmic number of steps. See exercise 1.16. Although, as is often the case with iterative algorithms, this is not written down so straightforwardly as the recursive algorithm.